an upgrade to 0.6, and why you should normalize your observations, coming up on Machine Learning Basics. Everyone, Blake here, and we are getting up and running with ML Agent 0.6. I've actually done one or two videos on 0.6, but I hadn't upgraded all of the previous work that we've done, so I've recently done that, gone through, done some retraining, make sure that everything seems to work, and we're in pretty good shape. Upgrading to 0.6 really wasn't that bad. I'll go ahead, let's open up one of the more basic examples, and you'll see the repo now has a bunch of different folders for things. So the lunar lander stuff, the number picker, we're going to talk about that a little bit more in this video. Camera observations, I have a very simple example. The curriculum and imitation learning haven't been upgraded yet. Some batch files, a bunch of convenience stuff in there, some common things like materials and whatnot that get used across, and some helpful URLs, and then the actual Unity ML Agents folder. So we're going to go ahead, hop into the lunar lander, simple scenario, and fire this bad boy up. Zoom into our simple game with our generic academy, and I believe, yep, it's set up to play right now. So very simple example, right? We have the red target, we have the white cube, and we're just trying to move the cube onto the target. Nothing more to it. You'll see 4 files in this. One is the scene file. One is the agent, right? So this is our simple agent for this simple scenario. And basically this agent, as we've seen in the past, right, doesn't do anything on initialization. On reset, you randomize where the marker is and where the target is, and then you make one observation. Every step you make one observation. How far am I from the marker? And then you take an action. And then the game learns to put the marker on the target. And that's all there is to it. So that's what's in that agent. This is a brain file. So these are new. It's a scriptable object in Unity terms. I'll show you how to set one of these up. But basically, it's an asset, much like a model might be an asset or something like that. So it stays down in the assets, and then you reference it from your scene. And this is a bytes file that has weights for a neural network, much like we got out of previous versions. So we'll see here we have our main camera, our directional light, so we can see what is going on. We have our game, where we have our game kind of container, and then we have the marker and the target. The marker and the target in this case are just passive objects that get moved around by the agent here. And so this was the agent that we showed right there. And that agent, you'll see in here, there is a spot for a brain. So that is where we make a reference to one of these brain assets. And then, let's see here, next steps, whatnot. So these are all settings that are default brain settings or standard brain settings. And then these are all of the settings for this particular example, setting weights and reward values, as well as which object is the marker and which is the target. And then the generic academy here, this is my empty academy script, right? It does basically nothing. It's just a default academy. You'll see in here this, when you put an academy in, and we'll do an example of this, it won't have a brain or anything attached with it, so you're going to have to add a brain, and that's when you drag and drop this brain in. Now, so most of this stuff, we're very used to using the scene hierarchy to look at things. Unfortunately, the big drawback with a scriptable object is that there are references from the scene to your assets, but the scriptable objects don't actually get instantiated in your scene like other things do. So you'll see a reference to the brain here, right? So you'll see a reference to the brain from the academy and from the agents. but both of those are referring to your assets down here. So your scriptable objects kind of live in prefab space, right? They're not in implementation space. They're not instantiated like other things are. So you'll find it down here. So if you need to make changes to your brain, it's a little weird. We're very used to going through the hierarchy and pulling it out, but really what you have to do is go to your hierarchy or go to the assets. You can double click on it in the hierarchy and it will take you to the proper place in the assets. So you'll see that this is a learning brain. You can drag a different brain in here if you want to copy the parameters. It makes it very quick and easy to instantiate more than one brain, or to create variants of a brain by being able to copy the parameters. And then we have the traditional stuff that we're used to seeing, right? The space size, how many observations are we making, how many actions are we taking, are they continuous or discrete? So all of that is here. And so, yeah, that's the biggest change. To create a brain now, what you do instead of having a script that you attach and reference, what you're going to do is you're going to come in and you're going to right click and then you're going to go create. And of course it's off the screen where you can't see it. Hold on a second. Let me see. I don't think I can do it through this window though. I wonder, they haven't put, yeah, it is not in that menu. All right, well, I am going to drag my window up here so you can see. So I right click, hit create, and then you'll see where it says ML agents. And so you have player brain, learning brain, and heuristic brain. So player brain, so all of these brains provide a unified interface between the Unity ML system and your game. So that if you want the player to be able to take control, that's when you use a player brain. If you want to write an algorithm manually, kind of like old school AI instead of deep neural nets, or if you were able to do, you want to be able to control with simple if-else statements or some other kind of dynamic scripting, that's a heuristic brain. But then when you want the agent in your game to be controlled by neural network that you've trained up, that's where you do learning brain. So you come in and you click learning brain, it will give you a new brain. In this case, I can drag my old brain over and say, hey, copy the attributes from that, and then you'll see that it's moved this over to continuous space and can be used. And then it also has a field for model, right? So that is if you have trained a model, if you've trained some weights from something previously, you can drag and drop them there. And so that's what this is. So I already had one. Or in the case where you don't have one yet, right, you have a fresh brain that you have not worked with, then you leave that blank until you're able to do your first passive training, and then you can populate that with a brain. So those are kind of the differences in 0.6. Not a big deal. I do like the fact that having distinct brains down here is a little bit more organized, but I also I do sometimes find that the routines working with the scriptable objects, having them down in asset space instead of the hierarchy, is sometimes a little weird. I forget about it. I was like, oh yeah, I got to go down to the brain down there and make changes to it. Again, all of these have been trained up in the lunar lander, so we have all of them. In some cases, I've been training them for a rather long time. So in this case, the 3-input game is trained over 10 million iterations, and so we have a pretty darn good 3-input brain. Oh yeah, there is one more thing I gotta show you. And so you can see it's playing the game and it's actually doing really, really, really well. Far better than I think any human could possibly do, for as difficult as this little game was. There is one more thing. In the Academy, when you add a brain, you'll see it here, right? And you can have multiple brains, right? So you can add yet another brain, and you can move the order around and whatnot. But one of the things that's important is when you are moving to go train your brain, you got to click this box that says control, and so that gives control over to this brain and says this brain is kind of in charge of the training process. So you'll start up the training script from the command line, and then it will prompt you to press play in Unity. And if nothing happens when you press play in Unity, it probably means that none of your brains have control. So you'll want to check that control box and then hit play again, and then it should probably work just fine. Let's see here. So let's take a look. We'll go into the batch file. So I've also added some convenient batch files. So we have two settings file. One is your machine name. And so this is for TensorFlow. Makes it easy so that I have a TensorFlow script I'll show you in a second that starts up TensorFlow and then opens up a browser to your machine, but it needs your machine name. So instead of trying to pull that out of a batch file or whatever, I just have a little settings file. My machine's name is Napoleon because all of my computers have been named after despots in history. And then the other one is your ML agents path. Where have you unpacked your ML agents folder, right? And all of that stuff. So you'll see here, and that's really handy because some of these batch files will open up a command console. I sometimes just get frustrated, like going and starting command, and then I accidentally close it, and it's in the wrong directory, and I have mine on another drive. And so just constantly moving around from directory to directory is a pain in the butt. So I just have one here where I have the start command. So I double click that, and it uses the current path for the project and then goes into assets and batch files. But then I can do something like start TensorBoard, and poof, that, as you see, will open up a command line, and that's going to fire up TensorBoard, and then it should go to my local machine. Sometimes what happens though is this opens up so fast it opens the browser so fast that TensorBoard hasn't had a chance to start. So you can also just double click start TensorBoard. Yeah, there we go, and you'll see, second time I started TensorBoard, it fired up a lot faster. And then you can see, there it is. Here's TensorBoard. We're going to talk about that in a little bit. So this is going to be an interesting discussion about observations. And then we also have this train command. The train command you don't want to fire up right from the Unity editor. The train command, because it needs a run name. So you can say train my thing -run 1 or 12 or whatever, and then we'll say starting Unity ML agents. And then behind the scenes, it's switching over to the path that we had talked about in your config. I also have a very similar batch file named identically in my Unity folder, because if you notice, if I quit this batch file, which it does not seem to be letting me do, which is interesting. I don't know how to make you quit. You'll see that the path we ended up with isn't actually the source path in my ML agents, but you'll see that I also have a train.bat file in there, so that I always just, instead of having the longer name with all the parameters and stuff, I just say train this thing with this run number. Makes my life a little easier. These are the batch files that work for me. By all means, modify them to your heart's content for your particular configuration or scenario. And clearly these are for Windows users. If you're on a Mac or Linux, you have a much better batch and shell scripting environment anyway. Go for it. But for Windows, DOS stuff, I find that those are just kind of convenient to have. Links, just a couple links. Let's see here. Okay, so Yeah, and common is just like materials, and yeah, the generic academy, which again, the code on this is super unimpressive. All right, so with that out of the way, we're upgraded to 0.6, or mostly upgraded to 0.6. So we got a couple more projects to get there, and then I also want to get the automation piece more ready for 0.6, because I was certainly could have made good use of that when I was learning more about normalizing observations. So I got a message from a gentleman that I've been going back and forth with a little bit with machine learning stuff. And one of the things that he said to me was very counterintuitive to me. And it was counterintuitive to them too. He said, I've been training my machine learning agents, and he says the scale, I'm doing this number picking, and the scale of the numbers has a significant impact on how well the machine learning agent trains. I said, that doesn't make any sense. And he says, but it was very clear that this was the case. And so I found that fascinating. And so here's a rundown of the problem. All right. So we have an array of 10 numbers, right? Now, the first time that I did this, I, by default, out of habit, had normalized the value. So when I initialized this array, and the one we'll be working with has 10 numbers, but this is good enough for now. Right, so when I initialized it, I took the index, right? So, 0, 1, 2, 3, whatever. And then I divided it by the max. So in this case, it was 10. And so that the actual values in here were 0, and then there were 0.1, 0.2, 0.3. So I always divided it by the max, not necessarily 10, but if I was doing with 5, it would divide by 5. So that the values in my array were always 0 to slightly less than 1, right? So in the case of 10 numbers, it was always 0 to 0.9. And then there was some discussion about distance and can we teach it multiplication? The answer is yes, you could. And so it takes a little bit more time, we thought, than just doing the multiplication for it. But actually, again, that was additional feedback. It said in some cases it was faster for it to learn multiplication than for us to teach it with things already multiplied, which was another thing that was really interesting. But the first problem here, and the one that I studied, I went a lot more in depth with, I did a bunch of runs, is, I have these numbers, and he said, 0.1, 0.2, 0.3, 0.4, and 0.9, and that works. But he said what was really weird is if the scale is different, right? Even though the distance between the numbers, or the numbers have the same kind of relative value distance for one another, it really impacts trading. And so he said, if I multiply it by 10, right, so instead of 0.1 through 0.9, right, so then it'd have, 0 to 90, that, the system is going to learn on this top scenario, it's going to learn how to pick the biggest number, right? So you have these numbers and it says pick the biggest one. And it's going to learn how to pick that biggest number if the range is between 0 and 0.9, then if that range is between 0 and 90. So if your range is 10, 20, and so on, it is going to learn how to find the largest number here slower than if you find if you try to figure out how to pick the biggest number out of this. And then if you go really big, right, if you go from 0 to 900, right, so if you multiply by 100, it basically doesn't train. He says the computer system, for some reason, the ML agent cannot figure out how to train at all. It doesn't know how to pick the biggest number if there's 10 numbers, 0, 100, 200, 300, 400, 500, 600, 700, 800, 900. Like, doesn't work. And I said, that's really weird. I need to see this for myself because that's very counterintuitive to me. And is there anything else that I can learn from this? So, spoiler alert, he was totally right. That is a thing. Why that's a thing, I'm not super certain on, although I am going to go into some of the metrics and numbers that I collected. But I'm going to pull this up, make this large, and show you some of the runs that I did. Now, let's see here. As one would expect, right, if you had, pick 5, right, so you have 5 slots, and then you have to pick one of the 5. As you would expect, my computer would take way too long. Oh, you know what? I think I closed my TensorBoard. Batch files, start TensorBoard, poof. There we go. Right, so this is pick 5. Pretty darn simple problem. Absolutely no big deal. And, in 30,000 steps, it was basically trained. And it could have gone up a little bit more, but whatever. And then if you're picking out of 100 spots, right, if you're trying to choose something 0 to 100, then that is a much harder problem. And it really had a hard time training. And that also makes sense, right? The reward is very sparse. You might not just happen across it, or the number of times you fail is going to far outweigh the number of times you succeed. So I ran a bunch of tests about how many numbers I should be looking at, and then I found 10 was a pretty good number, because here's over 50,000 iterations. Here's my training curve, and so it's a fairly nice training curve, and it doesn't complete so fast that you're like, oh man, that was only a blip in the radar and the tiniest thing to destroy it, right? I wanted it to take a little while to train, but not crazy amounts of time to train. And this is also done with, I believe, 10 simultaneous games. So fine, this looks good. And this is with a scale of 1, right? So this is, I have indices 0 through 9. And that is, when we make an observation, that is the observation that we make, a value of 0 to 9. If it picks the 9, if it picks the highest value, then it gets a reward of 1. So in all of these cases, it's picking the highest value and then gets a reward of 1. So the reward is identical in all of these runs, but it's just the observations that are different. So that's with a reward, that's reward of 1, scale of 1. So we said, all right, what happens if we then just multiply that index and make the observation, we multiply it by 5? And holy crap, it makes a huge negative impact. And I mean, this is no joke, right? And so by having this observation be 5 times larger, so from 0 to 50, or 0 to 45 instead of 0 to 9, the training got worse. That is all I changed. And I have the code there in the project. You can go try it yourself. Should be up on GitHub now, so you should be able to see. If we go number picker, number pick big numbers, and so you'll see this scene. Yep, 10 environments, and you'll see what's the scale factor, right? How many numbers do you have, right, in 10, and then what is the scale factor? And be sure, so the max numbers here needs to match what is in the brain here, the space size and the observation size, right? So you're making 10 observations, you can choose one of 10 items, and then this also has 10 items. So the scale factor is literally just multiplying the index by that number so that we can see how big it gets and what impact that has. So we said, well, all right, I was surprised. Well, only kind of surprised. It's confirmed what I had been told. And here's the thing is, I don't know really why this happens. There are some theories floating around, but if somebody has a definitive mathematic explanation of why this happens, I would be very interested in seeing what that is. Let's see here. So, of course, I cranked it up some more. Instead of multiplying all the indices by 5, I multiplied them by 10. And then if I multiply them by 100. So again, the scale of the observation, so this has nothing to do with rewards, this has nothing to do with the complexity of the problem. We're keeping the complexity the same, scaling the space of the observations has a huge impact on whether or not it is training or not. So I said, well, okay, what happens if we go the other way, right? What about 0.5? And well, that was interesting. We actually got better than 1 by doing 0.5. Now, we didn't do so much better that I'm going to say that this is a slam dunk, right? This is close enough that I could have just gotten lucky early on and it just happened to be a better training run. Maybe, maybe not. You know, you could do multiple runs and get some statistics out of it. So these are pretty close. But again, I mean, these other ones are just way out there. So, all right, well, I'm going to keep going, right? So instead of scaling my indices by 0.5, I'm going to scale them by 0.1, right? And then, so now we start degrading again. And so that's interesting. And then as soon as we get to 0.01, the poorness of the training at 0.01 versus 100 is indistinguishable. So what does this tell me? This tells me that under the hood there is some mechanic that is favoring values in the -1 to 1-ish range is my guess. And that would be fairly normal for these kinds of tools because when you're dealing with floats and whatnot, they tend to have standard distributions, normal distributions, sorry. And so you'll get bell curves, and so it will tend to favor that. That is my intuition, but I don't have hard numbers on specifically why this occurs in such a discrete problem. Now, I did also go in and do some more numbers, so, and then I did spreadsheets because I am a nerd. Hold on. Where are, yes, machine learning choices at scales. So, waiting for the chart to show up. Okay, so I wanted to get a little deeper into what the heck is it doing? Why is the engine doing this? And again, I have some data about it. I don't have anything super definitive where like, that's it. But here is the histogram. So this is trained at 1, right? And then I'm running the program, and what I'm doing is I'm watching, now that I've trained it up, I'm playing the game, and what choices is it making? Now, in theory, right, these are the indices that it's selecting, not the values, right? So what index is it selecting, and why is it selecting? And, well, not why is it selecting, because we don't know why it's selecting it, but what index is it selecting? And every time that it runs, we should have a different index, and because of the way that we're shuffling the numbers, the highest value should be in a random index, and it should be evenly distributed across all possible indices. And so that's exactly what we're seeing here, right? Is we have a capable player playing this game, and that the value that we're looking for is generally evenly distributed, plus, you know, a little bit of variance because the numbers are random. But generally evenly distributed into each of the buckets. I'm like, okay. So then I ran it again. It scales 0.1, right? That's the one that trained more poorly. And I said, what bucket are you selecting? And the answer is, I am selecting the middle index much more often. And we're getting what really looks bell curve-ish, especially on the left, maybe on the right. Maybe we could run this a whole bunch more times to see if you get a real bell curve out of it. Or again, this is coming out of a neural network, so it might just be a little lopsided, but it is absolutely favoring the middle indices over the other indices. So this one did not train well and favors the middle of the possible range. And then for the 0 to 100, for the scale of 100, not 0 to 100, I asked the system, what indices are you picking? And it only ever picked index 1 or 2. And that's weird. And I don't know why that is. That is really weird. Why would it never, again, this is after the training that I've done, and it figured out very poorly. Its strategy was to only ever pick index 1 or 2, and usually index 2, not 1. And I don't have an explanation of why that is. Again, I did see, though, this bell curve, and I did want to dig into it a little bit. And so when I did, I wanted to understand a little bit more about the math behind the random numbers that are being used in ML agents, because that might help us understand a little bit more about what is going on. So the first thing I did was I used Unity's built-in random.range. And I said, give me a histogram of random.range. I want to get a general idea. If I ask for a float between 0 and 1, what the heck do I get out? The documentation says it should be a generally linear distribution. Then I look at the output, and it looks like a generally linear distribution. Again, it's random, so you're going to get some noise and variance in there. But and it is a game random number generator. It is not a true random number generator. So it's not going to be like super awesome random data, but this is perfectly reasonable and is just fine for many, many purposes. And I trained a brain in Unity. I created a brain, and I said, here's a game where no matter what you do, I'm going to give you a reward of 1. And then I went to go train that brain, and instead of actually really training the brain, I just recorded its initial reactions to stimuli. So basically, with an observation that was meaningless and a reward that was meaningless, give me out what kind of random actions are you generating? What kind of actions are you trying to take? That's the wrong one. And so here's what I got out of it. I said, from 0 to 1,000, just give me a number. And it was, again, roughly even distribution across the space. I do feel like there might be, kind of a bit more variance among some of these than I would really expect for that. But again, this is a very noisy system. This is a randomized, uninitialized, basically, neural network. And so it's probably going to favor some things more than others. So that may be just what we're seeing here is kind of by virtue of the network, being uninitialized, but still just being initialized with some bias, because you normally seed random weights when you're creating a brand new neural network, as opposed to starting everything at 0, because that's far too ordered and introduces bias. And then so I did the same thing, and I said, but instead of discrete space, give me continuous space. And this was really interesting to me because this is a beautiful normal distribution as opposed to a linear distribution. And so this says to me, if you have a neural network and you initialize it and you say you have one continuous action, these are the numbers that you get out of it. Now, what's also interesting about this is I do not believe I bounded this output from 0 to 1. So this is by nature of these networks, this is a normal distribution from 0 to 1. I'm sorry, from -1 to 1. This is what the output is going to look at first. And so it is going to search this space, right? It's going to try things, it's going to try actions in this area, in this range, more often than it's going to try these extreme actions. And if it is not given reason to, it will likely not explore out well beyond 1 and -1. And so we've kind of talked about that with normalizing your actions. You want to normalize your actions to either 0 to 1 or -1 to 1. And this is a large portion of the reason why. And I think that because, again, we have these statistical engines that are kind of behind this, that may also be driving part of what is causing these very, very large observation spaces or very, very small observation spaces. Even though the number of observations are the same, the ranges in them are very different. And so I think that there's probably something like this driving the system, or something Gaussian driving the system. And so it's looking in this range, right? So if we also said, well, -1/2 to 1/2, right? That's the vast majority of this, and then it doesn't have to look outside of these ranges, and so that might also be why it trained faster on that. So I bet under the hood we have one of these bad boys kind of driving the show. So when you can, normalize your observation space to a -1 to 1 range or 0 to 1 range. It might benefit you a little bit to do like 0.5 to 0.5, but that gets sometimes the mental gymnastics to do that, depending on the problem, can be a bigger headache than it's worth. But certainly -1 to 1, there's clearly some value in kind of bounding the ranges of your observations so that it takes advantage of how the ML agents works under the hood. So I thought that was interesting, certainly worthwhile sharing, because I didn't know any of that going into this. And so now I know, and because I know and you're watching this, now you know. So that is pretty much all I had for today. If you have any questions, thoughts, comments, please feel free to leave them in the comments below. If you want to support the show, then a like, a share, or if you've really gotten a lot out of the show, then please, by all means, go visit my Patreon page and help out there. In the coming weeks, I'm hoping to put together another intro video to welcome. There's a ML Agents Challenge coming up for the random tower that they're putting together. That launches February 11th, so I am expecting a bunch of people learning more about ML Agents. So I do want to have a video welcoming that aboard, and then I do also want to get into camera observations and improving the automation. Because working with the scale stuff, this would have been a great one to have an automated system be like, okay, try it at 1, try it at 10, try it at 0.1, without me having to manually do stuff and then run them. So I do want to get my automation back up in version 0.6. So in the meantime, you know where to ask questions. Hopefully I'll be able to provide answers. And thank you so much for watching. Good luck out there and happy learning.